This video details the development of a high-temperature resilient magnetite ultra-high-performance heavyweight concrete, or UPHWC, shielding jacket. Our goal is to strengthen nuclear reactor containment structures under severe thermal loading, bridging the technology readiness level 4 to 7 gap through the Strategic Research Fund. There is a critical need because standard nuclear concrete degrades and risks catastrophic failure at temperatures above 300 degrees Celsius. Our proposed innovation, Magnetite-UHPHWC, offers superior gamma and neutron attenuation up to 800 degrees Celsius and maintains high strength. We ask for 36 months of R&D to deliver a fully validated operational prototype, achieving sovereign IP and elevating Malaysia's technological readiness. The global nuclear shielding deficit is significant. Nuclear energy is critical for net zero targets, but existing biological shielding fails under prolonged thermal stress. Standard operating temperatures from 65 to 150 degrees Celsius drive degradation, while extreme events can exceed 1,000 degrees Celsius, causing total structural breakdown. 31 nations currently require continuous shielding integrity. This vulnerability heat map shows the failure of conventional concrete. The critical threshold is 300 degrees Celsius, where barite concrete suffers sudden thermal expansion, catastrophic spalling, and a 9.92% drop in radiation attenuation. Beyond 400 degrees Celsius, it enters a failure zone, leading to total structural breakdown around 800 degrees Celsius. Our proposed innovation is thermally resilient UPHWC. We engineered thermal immunity by synthesizing ultra-dense magnetite aggregates with precisely calibrated nanoferrosilicon. This formulation withstands 800 degrees Celsius without sacrificing structural integrity, delivering high gamma attenuation, neutron absorption, and thermal resilience. The ultimate shield has 5 key components. Silica fume and Portland cement form the binding matrix. PVA and steel fibers act as a tensile skeleton, preventing fracture and spalling. Nanoferrosilicon is a micropore filler and densifier. Colmanite powder is a specialized neutron absorber, and magnetite aggregate, the primary core, is a high-density gamma-ray blocker. The nanodensification mechanism is crucial. Traditional concrete under high heat develops large voids, leading to microcracking and spalling. Our nano-modified UPHWC uses nanoferrosilicon to physically pack the interfacial transition zone. This ultra-densification prevents crack propagation and effectively traps radiation, even when heated. The aggregate performance matrix shows the magnetite advantage. Compared to sand and barite, magnetite has a much higher density, is stable up to 800 degrees Celsius, and offers 22.5% higher gamma attenuation and 17.6% more effective neutron shielding than barite. Magnetite decisively outperforms traditional aggregates across all critical metrics. Visual proof confirms the thermal resilience of our magnetite concrete. At 800 degrees Celsius, ordinary concrete and barite concrete exhibit severe cracking, catastrophic spalling, and total structural destruction. In contrast, magnetite concrete remains intact with preserved structural capacity and smooth surface geometry. We've achieved unprecedented mechanical and shielding milestones. The compressive strength reached 189.8 megapascals, significantly higher than standard concrete's 30 to 40 megapascals. The maximum linear attenuation of 0.240 centimeters minus 1 means a half-value layer of just 2.88 centimeters, drastically reducing the required thickness for biological shielding walls. Our rigorous validation methodology includes 4 levels: material characterization, prism and coupon program, structural wall strips, and a final prototype demonstrator. All testing protocols align rigorously with international standards for high-temperature exposure and nuclear radiation attenuation validation. The certified radiological testing apparatus ensures safety and high-precision measurement. Using an enclosed cobalt-60 radiation source and lead shielding, the UPHWC specimen is tested in the narrow beam path, a scintillation detector and counter-capture transmitted photon energy to calculate the precise linear attenuation coefficient. The 36-month implementation roadmap escalates from TRL4 to TRL7. Phase 1 focuses on lab validation, confirming optimized mixes. Phase 2 involves severe thermal conditioning and shielding verification. Phase 3 culminates in structural wall strip casting, the prototype demonstration, and commercialization planning. Comparing the status quo to our proposed nano-modified Magnetite-UHPHWC highlights the strategic value. Traditional concrete fails at 300 degrees Celsius, while our solution maintains integrity at 800 degrees Celsius. UPHWC offers nearly 4 times the compressive strength, eliminates radiation leakage risk, and provides ultra-durable, cost-saving life cycle value. Our project aligns with Dana PMACU 2.0 and national ROI goals. We directly target MISTI advanced materials priorities, generating sovereign intellectual property through proprietary mix designs. The commercialization roadmap addresses the critical market gap for next-generation small modular reactors and medical radiology facilities, delivering a fully validated prototype at TRL7. The Dana PMACU 2.0 Strategic Research Fund is the catalyst to bridge the Valley of Death. Full funding for this 36-month proposal will transform laboratory-proven chemistry into a TRL7 operational prototype, positioning Malaysia as a global pioneer in advanced, thermally resilient radiation shielding. Our investment ask is RM 788,200.